Could 2 points on opposite sides of Earth share the exact same temperature and pressure? These are antipodal points, x and negative x, sitting directly through the sphere's center. We represent this as a continuous function f, mapping the sphere to 2 values. The Borsuk-Ulam theorem claims a matching pair always exists. To see why, let's simplify Earth to just the equator, which is a one-dimensional circle. Pick any point x on this ring, and its antipodal point, negative x, directly across the center. Now we define a helper function, g of x, as the temperature at x minus the temperature at negative x. Crucially, if we swap the points, the sign of the difference simply flips. If g of x is positive at one spot, it must be negative at the opposite side. Because temperature varies continuously, the graph of g must cross the zero line to get from positive to negative. This is the intermediate value theorem. At that crossing point, g of x equals 0, which means the temperature at x is exactly equal to the temperature at negative x. The match is mathematically guaranteed. We just saw that on a one-dimensional circle, at least one property like temperature must match. But the Borsuk-Ulam theorem goes much further, scaling this logic to any dimension. For Earth, a two-dimensional sphere, we track 2 continuous scalar fields, temperature and pressure. We define a mapping f that takes any surface coordinate and outputs its corresponding point in r² space. The theorem guarantees there is at least one pair of antipodal points, x and negative x, where both temperature and pressure are identical. Continuity forces these 2 independent values to sync perfectly. Imagine a balloon representing the sphere. To map its surface onto a flat table, you must flatten and compress the 3-dimensional object into 2 dimensions. This process inevitably forces the space to fold. You cannot avoid it. That fold ensures that at least one pair of opposite points will overlap perfectly. The Borsuk-Ulam theorem proves that continuity forces these hidden symmetries in our physical world.